thermodynamic processes happen in one direction. It seems like everything is just always tending toward equilibrium. So heat flows from hot to cold and not from cold to hot, and all kinds of other things. They only seem to flow in one direction, which is from a state of like less equilibrium to a state that is more equilibrium. Everything is dispersed evenly. So why does that happen? Well, we don't know just yet, but we're going to try to answer it. That's a question. So this type of process is called irreversible. This is just some vocabulary. But really, these aren't necessarily like prohibited that it goes the other direction. It's just very, very ... insert many varies improbable that it happens. And we'll try to figure out exactly why. But basically what happens here is that you have a collection of the possible ways that energy can be dispersed in a system. And it just so happens that if you count the number of ways that are possible to distribute the energy, the equilibrium state happens to be the one that has the most number of ways that you can find something that satisfies that macro state. And we'll develop that language a little bit, but just to tease you a little bit. Okay, so how do we count the number of ways that something happens? How to count number of ways to arrange something. And so counting the number of ways to arrange a system, to arrange the units of energy in a system, the units of something in a system, will end up being exactly what we mean by the statement here, being very, very improbable. This type of mathematics is called combinatorics. And this is a really general term which encompasses many, many, many fields. So don't take what we're discussing here to be the entire mathematical field of combinatorics, or even a very good glimpse of it, but that's generally what this is called. So here let's consider a two-state system. And so the easiest example of a two-state system, one of the easiest examples, is just a coin flip. So you've got a coin, you toss it, it lands, and let's assume that it never lands like on its edge or anything. It always lands either heads up or heads down. Okay? So what if we flip 3 different coins? They're all unique. Well, how many outcomes are possible if we do this? And so to figure that out, let's just build up a little bit. So let's start with 1 coin. So how many different ways are there to flip a coin? Obviously, it can either be up or it can be down. That's easy enough. Coin 2, how many different ways can we do it? Anybody, quick. We have 2 coins. We can have up just 2 ways. So we can have up, up. We can have 1 up, 1 down. They're both different. So we're able to decipher the difference between them, just so you're aware. So there's actually 4 ways. So we could set up all these different states and they all count as different outcomes, right? So now what about, so that's 2. That's 4. Maybe you can start seeing a pattern at this point. And I'm probably not going to write all of this out, but does anybody have any idea how many ways we could arrange 3 coins? Let's flip that down, flip that one up, shout it out as I'm going, and I'll just stop whenever somebody gives the answer. 3 ways? Not exactly. So You notice that the number of ways that you can, number of outcomes you can get actually increases as you increase the number of coins, right? So yeah, I should be writing coins plural equals that. So in this case, we have 1 coin. In this case, we have 2 coins, represented by the ups and the downs, meaning heads up and heads down. Here, there are 3 coins. So if we flip 3 coins, we can either get them all heads up, we can get the first one up, the second one down, the third one up, the first one up, the second 2 down. We could get what? We could get the first one up. Oh, I already got that one. We could get the first 2 down, that one up. We could get the first one down, the second 2 up. We could get that one down, that one up, that one down. Get that one up, down, up. Did I get them all? 1, 2, 3, 4, 5, 6, 7. Which one did I miss? Somebody help me here. I think I missed. Oh, duh. All down. So there are 8 ways, right? And so if we continue this logic, does anybody have an idea how this might generalize if we have, for example, just n coins? So it looks like what we're doing here is, so this is 1 times 2, right? Equals 2. This one is 2 times 2 equals 4. This one is 2 times 2 times 2. So it looks like maybe this is going to be like 2 cubed, really. And if we generalize to n, here, let me go to the next page. So if we have n coins, maybe it looks like this should be to the n ways. Does that seem right to everybody? And so generally, this is correct for the 2-state system. So you have a bunch of different systems. They're all separate and unique, and they have 2 different states, and you have n of them. There's always going to be 2 to the n ways that you can arrange those states. Okay, so in general, though, this will just look like the number of ways to do it is just going to be the number of states to the number of objects with that number of states. And then if you had another system that had, let's say, some other number of states, you would just do the same thing of states. And then it would also be to the exponent would be just the number of objects that there are with that number of states. And you would just do that forever until you get however many different systems you have in contact here. So for us, the 2-coin system, it only has 2 states. And for the first situation, we only had 1 object, so it was 1 coin, so it's 2 to the 1. The second system, we had 2-state system as well, but now there were 2 coins, so there were 4. Second, or the third one, 3 coins, was also a 2-state system, but now we had 3 coins, so it was 2 to 3. So 2, 4, 8, and now you could calculate it forever if you wanted to and had the computing power. Now also, if the coins are what we're going to call fair, and fair here just means that here P is what we're going to just loosely call the probability function. So it's just going to be probability of the state being up is equal to the probability of the state being down. Just basically that either up or down is equally probable. That's all we mean by the coins being fair. So if the coins are fair, do we have any ideas how we might calculate the actual probability for one of these, for finding like one of these specific states down here? So for example, let's calculate P of, and let's consider the 3-coin system again, but let's find exactly what this is. Well, no, let's not write it quite like that. Let's say the probability of 2 heads, 1 tail. Okay. Well, how many different ways are there to get two heads and one tails? Well, we can do this. We can do this. And we could also do this. Right? So there's three ways that we could arrange these coins such that we get two heads and one tails. Okay? Now, previously we had just shown that for the three-coin system, there are 8 states total. So we have 3 states here, which correspond to this. And we have 8 states total. The system overall, it has 8 total states. So if all of these states are fair, then what's going to end up happening is that the probability of 2 heads, 1 tails, is just going to be equal to the number of ways you can make 2 heads, 1 tails divided by the total number of states in general. So it's just 3/8. Does that make sense to everybody? Are there any questions at all? Oh, yeah, I see some chat. Oh, people were answering. Carter 2 to the n steps ahead. I assume that was supposed to be a joke. Okay. Now, okay, so we know the probability of getting 2 heads and 1 tail, right? What is the probability? Oh, dang it. I already ruined it. I should have just said what was the probability of getting 2 heads. Now you're already going to know the answer, but let me just do it anyway. So what's the probability of 1 tails? Anybody? It's the same thing, right? Because as soon as if you know the number, yeah, we are recording. Good call, Carter. We are recording though. So if we know the number of coins overall, so like we have n equals 3, and you stipulate that you want to consider the state that has 1 tails, well then 1 tails is the same thing as 2 heads, because the number of heads and number of tails are connected to each other by the number of coins that there are in general, right? So this is just the same thing. So p of 1 tails equals 3/8 as well. And so in general, we'll just either use like one or the other, like heads or tails, to stipulate what state you're trying to consider here. So just realize that you don't actually need to write both of them to uniquely decide what state you're talking about. All right. Okay. So now we're going to develop a little bit more language. So we have 3 states. Up, up, down, up, down, up, down, up, down. Whoop. That's not right. Down, up, up. These correspond Okay, so our language for this is that these guys right here are going to be called microstates because they're the kind of micro level happenings of what's going on in the system. And the single overall state, for example, like 2 heads, is going to be what we call a macro state. All right, and a little bit more language that we need to develop. So the number of microstates corresponding to a macro state is what we're going to call the multiplicity. Of a particular microstate. Sorry, macrostate. So this is the verbiage we're going to use here. And so in general, the way we would want to write this is we want to write multiplicity as a function of a macro state. So we would put, for example, 2 heads in here. We know that there are 3 ways to do this. The general notation we'll use is that this is equivalent to saying that omega of 2 heads is equal to 3. So we'll just use omega to refer to the multiplicity of a macro state. Okie dokie. And so now using this notation, we can conveniently write the probability of, for example, in this case, x heads, where x is just some variable, as being equal to the multiplicity of x heads. So in the example before, if we wanted 2 heads, we would put in 2 here, you get 3, over the multiplicity of all ways to arrange the system. So in the previous example, this would be 3, this would be 8. Okay, so this is the probability of macro state. All right. So now we're going to address the question. I should probably just go to a different page. How do we generally write omega of x? All right, now to figure this out, what we're going to do is we're going to consider 100 coins. Okay, 100 coins. Now, what is the total number? How would I determine the total number of microstates corresponding to the system? We had written it before in general, right? I think it was Carter who wrote the 2 to the n, so we'll assume he's still saying that. So the number of microstates, the total number, is equal to 2 to the 100. How big is 2 to the 100? Well, it's pretty big. It is 1.27 times 10 to the 30, not 38. And just a neat note is that if this were in units of kilograms, this would be roughly the mass of our sun. Because the mass of our sun is like 1.99 times 10 to the 30 kilograms. So just to get a ballpark feel for how big this number actually is. Okay, so that's the number of microstates. What's the number of macrostates? Anybody? Anybody at all? So the number of macrostates, remember, is basically saying like 1 heads, 2 heads, blah, 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 whatever. So we could have, yeah, exactly. So there's, and the reason it's 101 rather than just 100 is that you can count 0 heads, and then from there you've got 1 to 100. You've got 1 heads to 100 heads, right? So it's 100 plus 1, 101. All right, everyone cool with that? So this is 0 heads, oh, not omega, 0 heads, 1 heads, dot, 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 on to 100 heads. So that specifies all the different macrostates that you could have. So how do we possibly calculate the multiplicity of each of these macrostates from this 1.27 times 10 to the 30 number of microstates? Obviously, the technique we were using just before isn't going to work because we've just got so many. We don't want to have to do this by hand, like counting on our fingers or something like that. It's going to be a horrible, horrible time. So let's try to figure it out. So let's say we've got the 0 heads macro state, and I won't even put macro state. It's just assumed that if we say 0 heads, we're talking about a macro state here. So every coin is face down. So how many ways? What's the multiplicity of this macro state? It's just 1 way, right? That's easy enough because there's only one way to arrange them all face down. One head. Well, now you can start off with the very first coin being heads up, and you can just keep on moving that down one, down one, down one, down one until you get to the very last coin. So in this case, you have sigma of 1 heads is going to be 100 different ways. Does everybody see why that is? If anybody doesn't, shout out and we can draw some stuff, but I think it makes sense. So what about 2 heads now? Well, the way to think about this is start off with the first coin. So you've got 2 coins that you can make heads. For the first coin, you have 100 different choices, right? You can put it in any of the 100 spots that the 100 coins occupy. For the second coin then, after you've already chosen the first coin, now one of those 100 spots is taken up, right? It's filled by that first coin that you've flipped to heads. So now you only have 99 choices. And then you would think, well, it's just going to be 100 times 99, right? Wrong. So in this case, at least, the macro state is insensitive to the ordering here. So it doesn't care if you're doing one heads first and the other heads first. In this case, you could flip them, and it's going to be the exact same thing. So we're overcounting here by a factor of 2. So what we really want is to write this would be still what we were thinking, 100 times 99, but you want to divide by the number of ways that you can flip the coins, okay? So in this case, it's going to be 2 ways. Just because you've only got 2 coins, you can only flip them once. Flip them twice, I guess. And so in general, this is going to be, well, not in general, for the specific 2 heads macro state, there will be 4,950 different ways that you can do this. Oh, Kidok, does everybody follow why we're dividing by the 2 here? That's important. Yeah. Yeah. Well, so I mean, the key thing here will be whether you're considering a system of identical objects or a system of distinguishable particles. And so we'll talk about that more as we get to like a little bit later in the chapter. But for now, you're just being told like you can flip these things and it's the same state. But in general, the distinction will be distinguishable versus indistinguishable particles, okay? And then even when we get to the quantum statistical mechanics, there will be 2 different types of indistinguishable particles, right? There will be bosons and there will be fermions. They're both indistinguishable, but they obey different statistics, and that's getting a little bit ahead of ourselves. But yeah, you'll be told for now. And if you ever have confusions, just ask. All right. So now what about the 3 heads macro state? Well, we can follow the same logic that we had here. So for the first coin, we have 100 choices. For the second coin, we have 99 choices. For the third coin, we have 98 choices. But again here, we're going to overcount. So we have to divide by the number of ways we can flip the heads, flip the coins that are heads. And so the way you should think about calculating this number right here, so before we just said it was 2 because there's 2 coins we can flip them. The way you should think about that division factor is as follows. So this is our numerator. We know that. So you have 3 choices. If you're looking at the 3 coins that are heads, you can pick which of them you want to put in first. There are 3 different choices, right? If you have them laid down on the table in front of you, you've got 3 coins. So you've got 3 choices to start off with. Then after you've selected the first one, now you only have 2 choices. So it's 3 times 2. And then after that, you only have 1 choice. So it's 3 times 2 times 1, which in general is just going to look like whatever this number is, factorial, 3 times 2 times 1, all the way down. So sigma, or omega, sorry, 3 heads, is equal to 100 times 99 times 98 all over 3 times 2 times 1. And that is 161,700 for our multiplicity for this macro state. So we could keep going on and on and on up to the 100th coin, but at this point we can pretty well generalize this result. Okay, so let's do that now. So the actual generalization here, maybe I should rewrite that just so you can see it for reference. So I'll rewrite this result. 8 over 3 times 2 times 1. Okay, so moving on to n heads. Let's make that a lowercase. It's going to be 100 times 99 times 100 minus n plus 1 all over n 2.1. So this is just generalizing what we showed up here. So we can show that it lines up. So if we set n to 3, this n becomes a 3, so that's 97. 97 plus 1 is 98. So the top will just look like 100 times 99 times 98. The bottom will look like 3 times 2 times 1. Okay, so at least fits for that, and it fits for the other two cases as well. Now, we just want to notice the following, which is that if we write 100 factorial, and here, let me just do a quick aside if anybody hasn't seen this before. So if you have n factorial, what that means, well, there's another way to define it as well using integrals and analytic continuation, but for now this is going to suffice. So it's going to be n times n minus 1 times n minus 2, and then you just keep on subtracting 1 and multiplying until you get to 1. So that's all that factorial means if nobody's seen it before, but I assume you have. So let's prove a little result right here. So let's say we've got 100 factorial. We've got 100 minus n factorial. Well, if we write this out a little bit, this is 100 times 99 1 all over 100 minus n times 100 minus n minus 1 times 1. So if we look in here, we could rewrite this somewhere as 100 minus n times 100 minus n minus 1 times all the way down to 1. So what we can do is we can line up some of the terms up here, this series right here, with the series that we see down here. And so this term would cancel with this term, and this term would cancel with that term. And it just keeps going and going and going until all of those terms are canceled. And all you really have is 100 times 99 all the way down to 100 minus n plus 1. And so via this result, basically, we can rewrite this numerator right here using this factorial result. So we'll do that now. Sigma of n is equal to 100 factorial all over 100 minus n factorial, and then times 1 over n factorial, because we had this in the denominator before. We just showed that the numerator is equal to this. And so we've got 100 factorial all over n factorial times 100 minus n factorial. So look at that. At this point, now you've generalized how you would find every single multiplicity for a macro state for the 100 coin system. Now we can even go another step. We can generalize to however many coins we want. So now our multiplicity function will be defined by the number of coins we have and our macro state, which corresponds to n here. So in general, we can probably see that this is just going to be capital N factorial all over little n factorial times big N minus n factorial. So this is what our multiplicity function in general look like for the two-state system. And so this is a really powerful result. But you might be asking yourself, well, hey, like flipping coins and all is cool, but who really cares about coin flips? Well, there's actually a physical model which looks, whose states look just like this. And so this is called the two-state paramagnet, apparently. But I'm more familiar with this being called the Ising model. And people might pronounce this differently. It might be called like Ising model as well. But basically, it's a simple model of ferromagnetism, which is just like permanent magnets, where you have particles that are arranged spin up or spin down in some external magnetic field. So basically, the way you generally think about it is you've got some ring of particles, could be as many as you want, and they all have spin, which is a quantum number, which is either up or down. So some of them are up, some of them are down, up, down, up, down, down. And you have this embedded in some external magnetic field. Let's say B, it points that way. Okay, so basically the energy of this system, the two-state paramagnet, is going to be determined by the number or the alignment of these spins right here, right? So there's going to be less energy associated with a spin that is aligned with B. If you've taken electrodynamics, which I think you all have, there's going to be less energy associated with that state, and there will be more energy associated with the ones that are anti-aligned with it. So these states, they look exactly like the flipping of coins. So I'm just throwing this out there as a real relevant result of this thing that we have right here. So if you ever want to dig into how the Ising model works and whatnot, it's a really interesting system. But we're not going to really discuss it a whole lot right here. We're going to move on to something that's a little bit more complicated in terms of microstate counting. And that is going to be called the Einstein model of a solid. Okay. So what is the Einstein model of a solid? Well, it's a system that is made up of particles, and those particles have some number of constituent quantum harmonic oscillators with, we'll just say, number of quantum All right, so if you've taken quantum mechanics, then you know that for a quantum mechanical oscillator, which ends up being just about everything, that the energy changes, they come quantized, right? That's like the fundamental result of quantum mechanics and why it's called quantum. They are quantized, at least in this case, as h times f, where h here is Planck's constant, the non-reduced constant without the 2 pi, and f here is the frequency of the oscillation that you're talking about. Okay, is everyone familiar with this result? I'm not going to prove it here because it would take way too long, but hopefully you are. So if we have a three-dimensional solid, then what we're going to do is we're going to think of there as being one oscillator per direction for each of the three directions. Ooh. Direction. All right. So then if we have n oscillators, then you can think of there as being n over 3 actual particles. So just think of this as like when we were talking about a solid before, like we talked about how we can model a solid as being just a bunch of point particles arranged in some kind of like lattice thing, and they're all connected via springs. So just think of, instead of it being like an actual classical spring, now you've got a quantum mechanical spring, okay? And so now these springs, they can only take energy in discrete units of h times f. So let's start with n equals 3. So 3 oscillators, or 1 particle, okay? How many microstates for each total energy? And let's picture these oscillators like this. So, I mean, you know that the oscillator potential, it goes like x squared, right? So we can write the potential as some kind of quadratic looking thing like this. And then the energy levels are just going to be denoted by these lines right here. So they go on and on and on, and they're equally spaced by some unit h times f, right? Boop, boop, boop. And we'll call this E equals 0, even though, as we all know, the ground state of a quantum harmonic oscillator is not 0, right? It's actually offset by 1/2 h omega. So, but we'll just label it as 0, E equals 0. It's got 0 units of energy if it's sitting in its ground state. Well, what are the number of ways we could arrange for E equals 0? So, E equals 0. How many ways are there to do that? Anybody? So we've got these 3 oscillators right here. There's only one way, right? The only way is that they all have 0 units of energy. So that's easy enough. Now let's consider the multiplicity of the macro state, E equals 1. So now things get a little bit different. So now we think of you have in your hand 1 unit of energy you can throw into either of these 3 oscillators. So you can either throw it in the first one, put it up to there. You can throw it in the second one, put it up to there. You can throw it in the third one, put it up to there. So there are 3 ways, right? Now let's move on to E equals 2. Now you have in your hands 2 units of energy. So with those 2 units of energy, you could put them all into just one oscillator each time. So you could put them all in here, put them all in there, put them all in there. You could distribute them, 1 in there, 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 and then 1 in there, 1 in there. If you count that all up, you get 6 different ways you could do this. And then going on, I'm not gonna go through exactly how that works, but you can do it on your own time. If you consider E equals 3, there are 10 different ways you can distribute it, and it goes on and on and on. So we'd like to do something like we did for the 2-state system just before, the simple 2-state up or down system, and generalize what this is. And so we're not going to give a very rigorous definition or derivation here, but eventually maybe we'll be able to do something like that. But for now, what we'll do is we'll write down the general result and then we'll just check it. So in general, we have n oscillators. And let's say Q represents our units of energy. Then this function looks like the following. It's a function of n and q. N is oscillators, q is units of energy. It's going to be called the binomial coefficient, where the top slot is q plus n minus 1, bottom slot is q. And this is just defined as the following: plus n minus 1 factorial all over q factorial times n minus 1 factorial. And so just a little aside about this right here, and something that I always really like to keep in my head when I'm calculating these, is that the way you can think about this in your head is if you have the following binomial coefficient. Let's say you've got n and you've got k. The way that I say this in my head, and the way that lots of people do, is n, out of n, choose k. N choose k. So the number that this gives you, it tells you that there are n choose k ways to choose an unordered subset of K from a finite list of n elements, basically. And so in general, how you calculate this is just given by this value right here. But this is what I say in my head every single time I want to actually calculate something. For example, putting in hard numbers. So if we have 3, choose 2. So you have a set of 3, choose 2. And what are the number of ways to do that? Well, let's write it out pictorially. So we've got 3. What the heck does that mean? Well, we'll have 3 dots. So choose 2 of them. Well, one way to choose 2 of them would be circle those 2. Another way would be circle those 2. And then another way yet would be just circle that one and that one, right? So there are 3 ways to do this just by our visual counting. And also, if we use this formula right here, the way this will go, it'll be 3 factorial all over 2 factorial times 3 minus 2 factorial. And it better give us 3 ways, right? So 3 factorial is 3 times 2 times 1, which is 6, over 2 times 1 times 1, so 2, equals 3. Okay? So hopefully this quick discussion about how to think about the binomial coefficient helps you understand what it's actually doing and how it's counting, why you get these numbers. So that's our time for today. I think we got about as far as I wanted to, so that's good. But I'll certainly be posting at least one asynchronous lecture this week, so keep an eye out for that, and I'll be posting the YouTube link as soon as that's up. And I did record all of today's lecture, so that'll be up as well. Your homework solutions are up, and homework 2 is up, so make sure to look at all of that. Are there any questions about what we just went through today? This is kind of when things start getting fun, in my opinion. Like the introduction to microstate counting is kind of my favorite part of statistical mechanics and thermodynamics. So I hope you guys are enjoying this so far. It'll get more interesting as we get to larger and larger systems of these Einstein solids, where you actually start to see microscopically why things are only ever found in equilibrium. And so that'll be a really cool result. All right.